In this lesson, I would like to take the concept of stereoisomers and push it a little further. So we need to expand on this idea and try to get a feel for how powerful stereoisomers are in terms of the way that chemists think about the world. So the first thing we're going to do is start off with this molecule right here. Just kind of ignore the rest of this for the time being and focus on this right here. This is a bromochlorofluoromethane. This represents a class of molecules called alkyl halides that you have not officially been introduced to yet. So if the name of this is something new to you, don't worry about it now. That's just what we call it. This is bromochlorofluoromethane. And I've shown it in a wedge dash diagram. So I put the hydrogen in the back and the chlorine in the front. Well, one of the things that we have here is a carbon with 4 different atoms coming off of it. And we'll find that when you have a carbon with 4 different things coming off of it, that carbon has some unique characteristics. In fact, that carbon is called a chiral carbon. This is one of the definitions that we need right here. So a chiral carbon is a carbon with 4 different things. Now, it could be lone pairs in some weird examples, but for the most part, these will be atoms with 4 different atoms, or we should say groups, coming off of it. Now, this is not a very technical definition, but this is essentially a working definition. You can identify chiral carbons when you look at a carbon and there are 4 different kinds of things coming off of it. And we'll see some more complicated examples of chiral carbons in a minute, but this is a simple one. We have a carbon with 4 different things coming off of it. When you have a carbon with these 4 different things coming off of it, when you have a chiral carbon, that means that it's going to have a mirror image that is a different molecule. So this line right here represents a mirror plane. Imagine that you were standing on the side of this molecule and you stuck a mirror up next to it, and then you wanted to look at what does that molecule look like through the looking glass? What is the mirror image of that compound? And so if this is your frame of reference and you're looking at the mirror, you have a hydrogen kind of poking forward, and the mirror image, that hydrogen would still be poking forward, and the chlorine is poking forward, and that chlorine is still poking forward, etc. So this right here is the mirror image reflection of this compound over here. And what we want to see is ask the question, is the mirror image really just the same compound all over again? So what I want to do is try to take this mirror image out of the mirror and set it on top of this compound. But if I do that, right now the fluorines don't match up very well. So what I need to do is spin the thing. So I'm essentially going to stake it down with a vertical axis like this that cuts right through that carbon-bromine bond. Try to get this moved over. Imagine that I were to stake this thing, pin it down, and then spin it. And it could freely spin, and the fluorine and the hydrogen and the chlorine just kind of run around in a circle like a merry-go-round. So I've staked this down and I want to spin it. When I spin it like that, and I spin it 180 degrees, this fluorine spins and ends up over here 180 degrees away from where it started. This hydrogen, which is currently pointing away from me, if I spin it 180 degrees, it will end up pointed towards me. And the chlorine, which is currently pointed towards me, if I turn it 180 degrees along this vertical axis, it'll end up spinning away from me. So what I've done right now is I've taken this molecule and I've drawn its mirror image, with this being the mirror right there, and then I rotated that mirror image so that I could try to overlay it on top of the original compound, and what you'll notice is it doesn't match. Sure, the bromine and the fluorine line up well, but the chlorine and the hydrogen are in different places. So this is what happens when you have chiral carbons. Carbons with 4 different things coming off of them have a mirror image that is actually a completely different molecule. These 2 compounds right here are not the same. They are different. They are stereoisomers of each other. The classic example of stereoisomers are your left hand and your right hand. So if you stop for a minute and just kind of put your 2 hands, spread out your fingers and your thumbs, and then hold the 2 hands up next to each other so that they're facing each other, And what you'll notice is that your hands are approximately mirror images of each other, assuming you're not missing fingers or whatever. Your hands are essentially mirror images of each other. And if you keep your left hand and hold it kind of stationary, don't move it, and then take your right hand and spin it 180 degrees. So currently I'm looking at my hands and both my thumbs are up, and my right hand I'm going to spin it 180 degrees by pointing my thumb down. And then I try to sit my two hands on top of each other. They don't fit. So my hands are non-superimposable mirror images of each other. Superimposable means that you can just take the structures and lay them on top of each other. And your hands don't match up. Your thumbs are now pointing the wrong way. If you take your hands, spin one of them 180 degrees without hurting yourself, and then just kind of sit them on top of each other, you'll notice that the thumbs no longer match up. In the same way, if we take the mirror image of bromochlorofluoromethane and then we rotate it 180 degrees, which is what we did right here, and then try to set those two images on top of each other, the thumbs don't line up. The chlorines and the hydrogens don't match. So in the lesson question, it asks to draw a wedge dash diagram of bromochlorofluoromethane, and that's this one over here. And then I drew the mirror image of it, the wedge dash diagram, and the relationship between these two mirror images, the relationship is that they are non-superimposable mirror images of each other. And rather than say non-superimposable mirror images of each other over and over and over again, that's what we call enantiomers. So enantiomers are stereoisomers that are non-superimposable mirror images. Chirality is a little redundant to define. So essentially, chirality is a property. It's a characteristic of having an enantiomer. So it's the property of having a non-superimposable mirror image. And since we can define non-superimposable mirror image as the word enantiomer, it's the property of having an enantiomer. So molecules that have enantiomers are referred to as chiral. Again, this gets kind of difficult, so we're going to ask a lot of questions of you of, is this molecule chiral? Does it have chirality? And the ultimate way to test for chirality is to draw the compound with a wedge dash diagram, and then draw the mirror image, and then redraw the mirror image rotated 100 degrees, and then try to fit the two mirror images on top of each other. And all of that ends up being quite a lot of work, and every one of those steps has a certain probability of error. So we need a simpler, a more easily workable definition for chirality, and so that's where the term chiral carbon is useful. If a molecule has a chiral carbon somewhere in the structure, then it's going to be chiral. So a chiral carbon is a carbon with 4 different groups coming off of it. And so if you look for a carbon that has 4 different things coming off of it, then that's a chiral carbon, and a chiral carbon will have an enantiomer because the whole molecule becomes chiral. There are some exceptions to that. Compounds that have internal planes of symmetry, which are words that don't have meaning to you right now, and we'll look at those later. But for now, at this point in your life, chiral compounds have at least 1 chiral carbon. So let's see some examples of molecules that are chiral, ones that we've actually already looked at. This compound right here is cyclohexane. All of the carbons in cyclohexane are methylene carbons, meaning that they are CH2 carbons. The definition of a chiral carbon is that that carbon has to be sp3 hybridized, so good. And so a chiral carbon has to meet 2 characteristics. It has to be sp3 hybridized, and it has to have 4 different groups. So these carbons are all sp3, so 1 for 2, but they have 2 hydrogens coming off all of them. And so they don't have the 4 different groups. So what about this one right here? Is this now a chiral carbon? And the short answer is no. So I'm going to call this a methyl group right here. And this right here is a hydrogen. This carbon has, it's sp3 hybridized, so that's good. It has a methyl group coming off. That's one thing that's unique. It has a hydrogen coming off. That's the second thing that's unique. And it has a CH2 group right here and a CH2 group right there. Now those two CH2 groups are exactly the same, and you know that only when you keep following them out. So this CH2 group is connected to a CH2 group. This CH2 group is connected to a CH2 group, and then both of them are connected to the same CH2 group. So these two CH2 groups are exactly the same. Well, that seems obvious. Well, let's come up with a case where they're not exactly the same. Let me put another group right here, and we'll just put a fluorine on here. Let's go ahead and draw in a hydrogen. So now this compound right here has two potential chiral centers. Let's evaluate both of them. I'm not considering any of these CH2 groups. They don't meet the second criteria. And since everything is still sp3 hybridized, I'm just looking for those four different groups. This carbon is bound to a methyl group, a hydrogen, and two CH2 groups, but those two CH2 groups are not the same. This CH2 group is connected to another CH2 group, whereas this CH2 group is connected to a carbon that's bound to a fluorine. So you have to keep following those carbons out until you find some kind of point of difference, or until the molecule just ends entirely. And in a chair conformation, maybe it's a little harder to see that. So let me show you the kind of the top-down view of this same chair conformation. And I'm going to put a methyl group here. Well, no, let's do it right there. Let me see. I did a fluorine on this one, so let me stick with the same example, and I'll put a fluorine going back down into the plane. So what I just did, imagine that I was standing right here above this molecule looking down on it, and what I drew here was just my top-down perspective of the compound. And while we really like this chair conformation for considering things like axial and equatorial, when looking at stereochemistry, often it's just a lot easier to do kind of this flat top-down view of cyclohexane. This carbon right here is connected to a methyl group. There's a hydrogen that I didn't show. Right there, there's my hydrogen. And then this CH2 group and that CH2 group are not the same. So that is a chiral center right there, because the two CH2 groups are bound to different things. They are not exactly the same, and so they're different. This is also a chiral center right there. And this one, we have a fluorine. Sorry, this carbon is bound to a hydrogen, a fluorine, a CH2 group, and a CH2 group. You can't stop just because these CH2 groups are the same. You have to keep going until the molecule ends, and you'll see that at this point, the two CH2 groups are bound to different neighbors. So that's a chiral center, and that's a chiral center right there. This molecule has two chiral centers. So now we see the problem that just calling something bromochlorofluoromethane actually specifies one of two different compounds. And we need a way of using a name in order to talk about which of those two compounds we want. And we can't use cis and trans like we did before when we were dealing with cyclohexane ring systems, because there's not really a ring, there's not a face of this one. So three scientists with the last names of Kahn, Ingold, and Prelog came up with a system they call the RS system of nomenclature. And this system requires us to reorient ourselves relative to the molecules. And so I'm just going to pick on, let me just kind of categorize these. I'm going to look at this enantiomer first, and then I'll come back and look at this enantiomer in a second. And what they did is they first established that every atom has priority. And the priority of an atom is proportional to the number of protons that it has. So the carbon is the chiral center. It's the sp3 hybridized atom that's connected to four different things. So I don't care about its priority. It's the thing I care about. It's the kind of the center point. What I care about is the priority of the four things that surround it. Hydrogen has one proton. Bromine has 35 protons. I'm looking at a periodic table right now. Chlorine has 17 protons, and fluorine has 9 protons. So because bromine has the most protons, it ends up being the highest priority thing coming off the carbon. And this has to do with just this particular system of nomenclature, the Kahn-Ingold-Prelog rules. Of the remaining three substituents, chlorine is the second highest priority, and then fluorine is the third highest priority, and hydrogen has the lowest priority because it has only one proton. That's the atomic number. The atomic number is the lowest. Now what I have to do is take this molecule right here and turn it so that I'm looking at a Newman projection that starts at the carbon and ends at the lowest priority atom. Let's pull up a ChemDraw 3D image of this compound. So here I have that same bromo-chloro-fluoromethane. Here is the carbon atom. This is the hydrogen, the fluorine, the bromine, and the chlorine. Notice how the halogens get progressively bigger as we go down the periodic table. Fluorine is the smallest, and then chlorine and bromine. And ordering these, bromine is the highest priority, and then chlorine, and then fluorine. And what I need to do is consider a Newman projection where that carbon, that is chiral, is in front, and whichever substituent is the lowest priority is pointing away from me. So this right here is the Newman projection that I want to see in order to use these Kahn-Ingold-Prelog rules. Now this is, again, a lengthy process and will require you to be able to flip molecules around in your mind fairly quickly. If you have a model kit, this is the section of your textbook where that model kit can be most helpful. I want to repeat kind of that same three-dimensional rotation exercise. So I'm going to take this compound right here. I want to leave those labels because I need those in a second. And I need to consider, kind of rotate this thing so that the hydrogen is behind the carbon. And that will give me a Newman projection. But the back atom, that hydrogen that I put in the back, doesn't have anything coming off of it. So it's kind of an abbreviated Newman projection right here, where this is that front carbon right there. That's the carbon in front, and that's the hydrogen in the back. And in order to get that perspective, I need to kind of, if you're standing at your computer screen, just kind of move your head up towards the upper left position of your computer screen and pretend like you're looking slightly down and to the right at this molecule. And when you do that, fluorine should be on your left hand, bromine should be coming straight up from that carbon, and the chlorine should be down and to the right. Now we have situated ourselves correctly to be looking at this chiral carbon from the correct perspective of the Newman projection. And again, if you're asking why on earth do we have to go through all these steps, well, Kahn, Ingold, and Prelog came up with a system that needed to be reproducible. And it has a lot of individual little steps, but you get used to it after a while. So we have a carbon in the center, fluorine down to the left, bromine on top, and chlorine down to the right. And now what we need to do is kind of think about the rotation. So we start from the highest priority atom, and you kind of rotate this towards the second highest priority atom, which is the chlorine, and then you rotate this towards the third highest priority atom. The directionality of this circle is labeled, in this case, R. That might come from the concept of kind of a right-handed circle. Usually we talk about this as being clockwise versus S is counterclockwise. And so in order to help you kind of figure out why R and S are important, let's look at this molecule now. And molecules that are enantiomers of each other should have opposite chirality. So if we're correct in calling this carbon up here that this is R, the chirality is R, then this carbon, which is its enantiomer, that non-superimposable mirror image, or the left hand of the right hand, then this one should be S. But we need to first verify that. So I need to look at a Newman projection so that this carbon right here is in the front. Let me get my Newman projection ready. So this is the carbon right here that's in the front, and there is a hydrogen in the back, and the hydrogen doesn't have anything coming off of it. So the hydrogen is just that great big circle in the back. Coming straight up off of this carbon. So in order to see that, you kind of need to move your head up to the upper right portion of your screen and pretend like you're looking down to the left. You're kind of rotating your head relative to the molecule. That puts the carbon in front and the hydrogen in back. The chlorine should be to the lower left. the fluorine should be to the lower right, and the bromine is coming straight up. Now we assign priority based on atomic number. Bromine has the highest atomic number, or the most protons. Chlorine has the next highest atomic number, so this is substituent number 1 based on atomic number. This is substituent number 2, and then that's substituent number 3. Notice how this now is rotating in a counterclockwise fashion. Okay? And sometimes they refer to this as kind of a left-hand rotation. And so this is where the term S comes from. I believe it's sinistra, which is left or something like that in some language. I think about it as a screwball. I'm a right-handed pitcher, if I did pitch. And if I throw a baseball and want to try to throw a screwball, you actually have to rotate your hand at the end of your pitch in a counterclockwise fashion. And if you've never played baseball, and if you're not right-handed, that's not helpful at all. So clockwise, counterclockwise, that's what we're stuck with. If the rotation from highest priority substituent to second to third goes in a clockwise fashion, it's R. And if that rotation goes in a counterclockwise fashion, then it's S. And the nomenclature, we just write that label out in front, italicized and in parentheses. So there is the name of this compound. It's R-bromochlorofluoromethane, and this is its enantiomer, which is S-bromochlorofluoromethane. And this gets us kind of to the perhaps even the easiest definition of enantiomers. Enantiomers of each other have opposite chirality labels. So if one of the carbons in your structure is R, and you redraw that structure, but you end up with the carbon being S, then if the only difference between the two names is R versus S, then those are enantiomers of each other. So I'm going to take these two images right here. This shows me the R-bromochlorofluoromethane and the S-bromochlorofluoromethane, which is what the lesson was asking for. Name both stereoisomers using the Kohn-Ingold-Prelog-RS notation. There is a story, and I don't know if it's true or not, but it's fun to tell, that Kohn, his initials were RS. And so he found a language where R and S worked such that he could use his initials as the way of identifying the system. And his particular rule system has been unpopular for centuries. Well, not centuries, for decades. Organic chemistry isn't quite that old. It's been unpopular for decades, but nobody has come up with a better system, and tradition kind of dictates that we use these R and S labels. For the next question, it's going to ask me to draw all stereoisomers of a molecule called 2-bromo-3-chlorobutane. And so here I have a wedge dash diagram of 2-bromo-3-chlorobutane. Here's the butane, 1, 2, 3, 4, the bromine at the 2 position, and the chlorine at the 3 position. Now I just kind of randomly assigned wedge dash diagrams to the chlorine and the hydrogen on carbon number 3, and the bromine and the hydrogen on carbon number 2, and we'll kind of deal with that in just a second. But you'll notice that this molecule has 2 chiral centers. This carbon right here is chiral, and this carbon right here is chiral. And the reason that it's chiral is because it met our minimum definition of chirality, in that it's an sp3 hybridized carbon, and it has 4 different things coming off of it. And I'm going to re-represent that carbon as a Newman projection. And so this chiral carbon right here is going to be that front point that has a red little box around it. That's the front carbon. And the back is going to be the lowest priority substituent coming off of this carbon. Currently, the lowest priority substituent coming off of this carbon is a hydrogen. The hydrogen doesn't have anything connected to it, so I'm going to trim this down a bit. And that circle in the back is going to be the hydrogen. Then what I want to do is try to look at this compound right here and figure out what's going to be at the top, lower right, and lower left. And hopefully you can kind of see that this molecule is already written in a way that is kind of a sloppy Newman projection. The carbon is kind of in front, that hydrogen is sort of in back, and so I can just kind of map everything onto this Newman projection right here. I have a bromine coming up off of this front chiral carbon, and then I have another carbon coming down to the right. This carbon over here has some stuff coming off of it. And then off to the left, I also have a carbon, and this carbon right here has some things coming off of it. So at first glance, it looks like the chiral carbon right here is connected to two carbons. And that's true, it is connected to two carbons, but those two carbons are not created equally. One of them is going to be higher priority than the other. And this is how you have to do this when you come to a situation where the chiral carbon is connected to two atoms that are the same, but as we move out, it does appear that those atoms are different. So it is a chiral center. Those two atoms are not exactly identical, but they are similar. And what you do is you make a list of what each of those atoms are connected to. I'm going to start over here because the list is fairly easy. It's connected to 3 hydrogens. That's what this carbon on the left-hand side is connected to, is 3 hydrogens. The carbon on the right-hand side is connected, and there's a lot of stuff coming off of here, but we only care about the atoms that are directly connected to it. So this carbon is directly connected to a hydrogen, a chlorine, and a carbon. It is also connected to that chiral carbon, but we're only looking at, we kind of already dealt with that. That's that bond right there. In order to do what I'm about to do, we need to come up with a list of the other things that that carbon is connected to. And the way I'm writing this right now is just the order that I'm kind of seeing it in. This carbon is connected to a hydrogen, a chlorine, and a carbon. But we want to rewrite this in order of descending priority. So in other words, of those 3 atoms, hydrogen, chlorine, carbon, I want to write the highest priority atom first. And the priority here has to do with the Kohn-Ingold-Prelog rules, where highest atomic number is highest priority. And that roughly approximates mass. So chlorine's bigger than carbon's, bigger than hydrogen. And so I'm going to take these 2 lists now and I'm going to compare them. I have them correctly written. I also have them correctly ordered. And I'm going to stack the 2 lists on top of each other so that I compare them based on the first point of difference. And the first difference that I see is the first atom. And this is why it's important to make that list in descending order of priority. The list on the bottom has a chlorine. The list on the top has a hydrogen. Chlorine beats hydrogen based on priorities, and therefore the carbon that's attached to that chlorine is a higher priority than the carbon attached to the hydrogen. And so I'm going to call this priority number 1, and this will be priority number 2, and this right here will be priority number 3. And like we did before, once you've identified the priorities, then you draw kind of an arrow to see from 1 to 2, and then 2 to 3, and the rotation of that arrow is going in a clockwise fashion. If something is clockwise, then that refers to the R configuration. Now, all of that work was to show you how to do that on your own. ChemDraw will actually just do it for you. If you've drawn a correct wedge dash diagram, you can right-click on the atom, show stereochemistry, and there's the R label right there. This is not a useful keystroke for you because it will not be available on the exams. You need to learn how to do it just like I did it over here. So we'll look at another example. For this carbon right here, the lowest priority substituent is the hydrogen. That hydrogen is already more or less pointing away from me. And if it's already leaning away from me, that's good enough. So I don't technically need to redraw it as a Newman projection. I can just call this chlorine would be the highest priority substituent. Of the 2 remaining carbons, this carbon's best substituent is a hydrogen. And this carbon's best substituent, the one with the highest priority, is that bromine. The bromine beats the hydrogen, and therefore this carbon beats that carbon. And so the chlorine is the highest priority substituent coming off of carbon number 3, the chiral center. This carbon over here connected to the bromine is the next highest priority substituent coming off of this carbon. And then the methyl group is the the third highest priority substituent coming off of that carbon. These arrows that I drew specifically refer to carbon number 3, not carbon number 2. We had to deal with those arrows separately. And this looks like it's rotating again in a clockwise fashion, so this should also be the R stereocenter. So I can put the stereochemical label on there, and yes, correct, it is R. ChemDraw got this one right. So what I've done now is I've come up with one of the possible stereoisomers for 2-bromo, 3-chloro butane. And this particular stereoisomer we can add the names to it. So it is 2R, 3R, 2-bromo, 3-chlorobutane. Notice the punctuation here that we put the stereochemical labels all the way out in front. We separate, and we number them when there's two of them. So we know which one we're talking about. At the 2 carbon, I have an R stereocenter. At the 3 carbon, I have an R stereocenter. And then the rest in the name of the compound. Now, in order to draw another stereoisomer of this same compound, all we need to do is grab one or both of these chiral centers and simply flip it. So instead of having the hydrogen go back into the plane of the screen and the bromine coming out, we're going to have the bromine going into and the hydrogen coming out. And it went ahead and auto-updated the stereochemical label. And this is always going to be the case when you just rearrange a chiral center. There's only two options. It's either R or it's S. If this is what R looks like, then this has to be S. And now this represents a different stereoisomer. Okay? And this would be the 2S, 3R, 2-bromo, 3-chlorobutane. And hopefully you see that we can continue, let's continue to work from the same original compound. If instead of flipping the 2 carbon, I now flip the 3 carbon, so I'm going to turn this into a chlorine. Notice how the stereochemical label goes away because now I have 2 chlorines on there, so it no longer meets the criteria of being a chiral carbon. It is sp3, but it no longer has 4 different things coming off of them. So the stereochemical label should reappear as soon as I put the hydrogen back on again. So what I did is I just flipped these two basically, and we saw the chiral center change, and that should give us yet another stereoisomer of 2-bromo, 3-chlorobutane. And the last one that I'm going to show you, and the last one that does exist, is where we flip both of these stereocenters. So I'll flip the hydrogen and the bromine, and then I'll flip the chlorine and this hydrogen right there. And so this should be the third one. And I'm going to check to make sure that the 2-bromo, 3-chlorobutane, yes, all of them say that. 2R, 3R, that's different than 2S, 3R, which is different than 2R, 3S, and 2S, 3R. No, I messed this one up. That's what I did wrong. This one should be a chlorine, and that should be a hydrogen. There we go. So RR, SR, RS, SS. They're good. We got them all. We got all 4 of the stereoisomers. Okay, that last bit of the video took me 5 takes, and I still got it wrong. But now we're good. We got them all. And the question you might want to ask is, how do you know that you have them all? And there is actually a formula that they have, and it's not too complicated. The possible stereoisomers that you can find for any compound is equal to 2 raised to the power of n. Well, what is the power of n? Well, n is equal to the number of chiral centers. Now, chiral centers is a more technically correct way of describing it because other atoms besides carbon can be chiral. But so far, the only thing that we're going to look at, and the only thing we will look at for the near future, are chiral carbons. So I'm going to go ahead and just refer to n as the number of chiral carbons, and then we'll update this later on when we start learning about other atoms that can also be chiral. So that means that if a molecule has 2 chiral carbons, then n is equal to 2, and 2 raised to the second power, you can pull out your calculator if you need to, but that's 4. And so I have my 4 possible stereoisomers right there. I delete all my outtakes immediately when they go wrong, just so I can't be held accountable for any words that might be said when I notice I make a mistake. Okay, so now we have kind of this idea of stereoisomers. But I want to introduce another idea, and this is kind of a Venn diagram. So if you think about the world, and it has all of these stereoisomers. So anything that is a stereoisomer should be inside of this circle. But stereoisomers are further subdivided into 2 different types. And one category of stereoisomer is a smaller category. And this is the one that we saw before. These are enantiomers. So this should be all stereoisomers can be thought of as being either enantiomers or not enantiomers. And it would be funny if that was the name, and it's not. So instead, we decided to make up a new word because not enantiomers is simply too easy. Diastereomers. And then we did kind of the rudest thing, and we went ahead and defined diastereomers. Diastereomers. It's equal to stereoisomers, and you're going to groan when you see what the definition is, that are not enantiomers. Seriously, that's what the definition is. Right? Diastereomers are kind of this other category. And so that means that we need a really nice and tight definition for what enantiomers are. And if you remember the original definition, it is non-superimposable mirror images, and then I immediately pointed out what a pain in the neck that is, because that means you have to draw the mirror image and then rotate it and see if it matches up. And so instead, we kind of have this poor man's definition of enantiomers enantiomers are compounds where all chiral centers are flipped. And I know I'm supposed to be using chiral carbons all the time, and we'll change that later, but I'm just going to stick with chiral centers for a while so we don't have to go back and change that. So let's look at which of these compounds are enantiomers of each other and which of them are diastereomers of each other. Now, if you want, you should pause the video here and see if you can come up with that answer yourself. Every pair should be either a diastereomer or an enantiomer, and using this definition down here, these definitions, you should be able to figure that out. Okay, let's see how you did. And if you got it wrong, that's because Brian didn't explain it very well. So first, let's look for the enantiomers. And the enantiomers we're going to define as compounds where all chiral centers are flipped. And I should emphasize this all, which is why they invented underlining. So all chiral centers. So RR can be flipped to SS, and therefore these compounds right here are enantiomers of each other. And you might also notice that a single molecule can only ever have one enantiomer. Enantiomers always come in pairs. They come in twos, because there's only really one way to flip all of the chiral centers. So this molecule has one enantiomer, and this is the enantiomer. This molecule also has one enantiomer, and this is its enantiomer. So it went from being RS to SR, and therefore these molecules are enantiomers of each other. So these arrows right here represent enantiomers, and that got kind of messy, but we're going to refer to these as the enantiomeric pairs. And again, the enantiomeric pairs are the upper left with the lower right and the upper right with the lower left. So these are the enantiomeric pairs right here. That means that every other pair that you can conceive of would be a diastereomeric pair. And so, for example, this molecule right here is a diastereomeric pair with this molecule over here because I flipped some but not all of my chiral centers. Notice how I flipped the chiral center at 2, but I didn't flip the chiral center at 3, and so they're not enantiomers of each other. They're diastereomers. When I was a student, the definition that the professor gave me for an enantiomer was non-superimposable mirror images, and I thought, oh, that'll be an easy definition to remember, and it was, but then when it came time for the exam, I had no idea how to apply that. Like, I tried to draw mirror images of it, and I wasn't good. And then I saw this definition for diastereomers, where it was stereoisomers that are not enantiomers, and I thought, well, I'm screwed twice now, because I don't know how to draw enantiomers very well, and so then I can't figure out what diastereomers are, so it was a lot of random guessing. So now, hopefully, what I've given you is a better toolkit, that enantiomers are where we flip all of the chiral centers, and this gives us then a definition for diastereomers that I like, that's a little bit more useful, are compounds where some, but not all, chiral centers are flipped. And hopefully you can already think of a case where the number of chiral centers can get really large. Like you can have 8 chiral centers, and 2 to the 8th is a big number that I need a calculator for. And so then to find all the diastereomeric relationships, you need kind of a quick tool to do that. You don't need to draw 2 to the 8th different molecules and their associated mirror images of each other. So I just go through and look at the chiral centers. If they're all flipped, then they're enantiomers. And if some of them are flipped, then they're diastereomers. So this pair up here is a diastereomeric pair. The pair across the bottom, they're also diastereomers of each other. This is RS, this is SS. I changed one, but not both of my chiral centers. And then the vertical pairs, these right here are diastereomers of each other, and these right here are also diastereomers of each other. So where are we at in this question? And the answer is we're now ready to answer this question. So what we've done is we've come up with all the stereoisomers for 2-bromo-3-chlorobutane, and for bonus points, we went ahead and found all of the diastereomers and enantiomer pairs. But now we need to come up with Fischer projections. And this should make you angry. This is where the history of chemistry has treated you poorly. And it actually has a reason. So a guy by the name of Emil Fischer, he was often considered the father of organic chemistry. He was looking at a lot of chiral compounds, specifically carbohydrates. And they have a lot carbohydrates have most carbohydrates that you're familiar with, such as glucose and mannose and galactose. They're going to have 4 chiral centers, and that's a lot. And then there's a lot of different stereoisomers you can draw. 2 to the 4th, that one I can do. 2 times 2 times 2. 16. You can have 16 different stereoisomers. And so they needed a way to draw these so that everybody could kind of be on the same page. So what a Fischer projection is, it is a set way of drawing a particular compound. And we're going to follow Fischer's rules so that when people draw this 2R, 3R, 2-bromo, 3-chlorobutane, everybody draws it the exact same way. And so to appreciate the genius of what Fischer came up with, I'm going to go ahead and move this molecule over to ChemDraw 3D. So I'm going to hopefully this, yep, I just cut and paste it into the palette right here. And that should look the same. And here we are. So this right here is now a 3-dimensional model of 2R, 3R, 2-bromo, 3-chlorobutane. We're just going to call this molecule A because that's less of a mouthful. So molecule A right here, what I want to do now is draw a Fischer projection of it. And what Fischer said for his projection was that you take whichever carbon is the lowest numbered carbon in your chain, so that would be carbon 1, and you kind of pick the molecule up by that carbon, kind of like grabbing a dead snake by the head. And so I'm going to reach into this screen and grab this carbon number 1 and essentially lift it up so that the rest of the molecule is hanging by carbon number 1 right here. And just kind of sitting there, just spinning dead guy right here. Okay? So I've got the entire molecule suspended by that carbon number 1. And with the Fischer projection, then what you do is you give each of the chiral centers kind of its moment in the sun. And in order to appreciate that, so I have carbon number 1 up top, and I have carbon number 4 on the bottom. Okay? So this right now is kind of the start of what Fischer wants us to do when we're thinking about Fischer projections. Now I'm going to come back to ChemDraw 2D and kind of show you what that looks like in a Fischer projection. Now a Fischer projection does not use any wedges or dashes. All of the wedges and dashes are assumed, which is awful. And so what I'm going to do is, because this molecule has 2 chiral centers, what Fischer's rules tell you is you just take any of the carbons that are not chiral, carbon number 1, which is not chiral, you just leave it as a list of atoms, just like this, CH3. And carbon number 4, which is not chiral, you just leave it as a list of atoms. But the carbons that are chiral, you draw them like a cross right here. So we have the carbon number 2 is chiral, so it's got something coming off to the left and something coming off to the right. And carbon number 3 is chiral, also has something coming off to the left and something coming off to the right. And for whatever reason, you don't bother to put the carbon label on those chiral carbons. It just stays like it is as a cross, and that right there is a carbon. If you want them in there, that's fine. People will laugh at you, but it won't be wrong. It'll just be weird. So we want to try not to be weird. So this is the way that we should kind of start the backbone of my Fischer projection. And now the last questions that I need to ask are, is this a hydrogen or is this a bromine? And therefore, is this a hydrogen or a bromine? And is this a hydrogen or a chlorine? Or is this a hydrogen or a chlorine? And I'm going to go back to the 3-dimensional model to kind of show you how Fischer wants you to look at this compound. Now you might ask, why does Fischer get to tell us how to look at these compounds? Well, he has one more Nobel Prize in chemistry than you do, so there's that. All right, so I've got this compound and I've picked it up by its head and it's dangling here. And the way that I look at this matters, because if I stare at the carbon strand just like this, then the bromine is on the left-hand side and the chlorine is on the left-hand side. But if I let it spin like this, then now the bromine is on the right-hand side and the chlorine is on the right-hand side. So I need to figure out which perspective Fischer requires me to look at. And what he tells us is you kind of need to think about where this carbon is relative to the carbon above it and the carbon directly below it. So this is the chiral carbon that I care about, and here is the carbon that's above it, and here is the carbon that's below it. Notice how if you draw a straight line between the carbon above it and carbon below it, this carbon is kind of puckered to the right-hand side. In a Fischer projection, you want to pretend like you're looking at it such that that carbon is puckered towards you directly. So right now, I am looking at carbon number 2 correctly, that it is essentially pointing at me. And again, to see why it's pointing at you, hopefully now you can see relative to carbon number 1 and carbon number 3, this carbon is pointing to the right. So if I swing it 90 degrees, now that carbon is pointing towards me. So I am looking at this correctly, and I can with confidence assign the bromine to the left-hand side and the hydrogen to the right-hand side. So the bromine goes over here, and the hydrogen goes right there. And students have done this, they forget to label the hydrogen because, well, it's a hydrogen and nobody cares. But then what's a line that ends in a point? That's a methyl group. And so you do need to put that hydrogen label on there so that you tell me that it's a hydrogen, because if you leave it unlabeled, I just think that you think it's a methyl group, and that's not what it is. All right, so now can't we just then put the chlorine on the left-hand side as well? And the answer is no. We need carbon number 3 to be pointing towards us. So the perspective that we need to adopt is we look at the carbon above. So now I'm moving on to the next chiral center. I'm asking what's going on with carbon number 3. I look at the carbon above it, and I look at the carbon below it, and currently, relative to the straight line of carbon 2 and carbon 4, this carbon number 3, the next chiral center, is puckered to the left. And so I need to turn it so that that carbon is pointed towards me, and that now puts that chlorine on the right-hand side. Yeah, but aren't the chlorine and the bromine on the same side? And the answer is not in a Fischer projection. A Fischer projection requires you to look at each carbon individually such that it's pointing towards you. Right now, carbon number 3 is pointing towards me, and carbon number 2 is pointing away from me. Okay? To kind of help you see what I mean by that, here's carbon 1, here's carbon 3. There's a straight line that connects them. Carbon number 2 is leaning to the right-hand side. If I rotate this in this direction, carbon number 2 is pointing away from me, and I'm looking at it backwards. So I don't need to worry about carbon number 2. I already assigned it. It's carbon number 3 that is currently pointing towards me, and the chlorine is on the right-hand side. So in the Fischer projection right now, the chlorine is going to be on the right-hand side. And this right here is a correct Fischer projection for this compound over here. We can double check that we've drawn the Fischer projection correctly by assigning the stereochemical label to the 2 chiral centers. And if they're both R, then we've drawn our Fischer projection correctly. I'll let ChemDraw do it for a second. Okay? There's R, and there's R. ChemDraw inherently recognizes Fischer projections. But now let's figure out why it's R based on the perspective. One of the things that you'll notice, going back to the 3-dimensional model, is let's now make sure that carbon number 2, the one with the bromine, is oriented correctly. Let's see, I want to tilt this just, nope. There we are. Now it's straight up and down. And it's side to side. This carbon right here is currently pointed towards me. Okay? So again, here's the carbon number 1, carbon number 3, straight line that connects them. It's puckered to the left. If I rotate it 90 degrees this way, now that carbon's pointed towards me, and I am looking at this correctly. What you'll also notice in this particular diagram, the way that I'm looking at it correctly in a Fischer projection, that hydrogen and that bromine are leaning towards me. So in this Fischer projection, you need to remember that the hydrogen and the bromine are both coming at you. Okay? If this was 3 dimensions, you'd see them poking towards you. Now let's remember that, but ignore it for just a second. Let's go ahead and just draw our circle in and figure out what it tells us. Bromine is the highest priority substituent. The next highest priority substituent is the carbon that's connected to the chlorine. And then the lowest priority of those 3, so this is highest priority bromine, and then next highest priority carbon, and then third highest priority. This is rotating in a counterclockwise fashion. And therefore, this should be S based on the arrows that I've just drawn. But wait, this hydrogen, if you remember, was actually pointing towards you. So rather than try to redraw the whole molecule so that the hydrogen is pointing away from you, just know that you're looking at it backwards. So in a Fischer projection, these hydrogens are coming towards you, and therefore you're looking at it backwards, so we need to flip those rules. If it looks like it should be rotating in an S fashion, reminding yourself that I'm actually looking at the wrong Newman projection. I'm looking at my Newman projection in reverse means that I need to flip the label. So if it looks like it's S, then it's actually R. So the labels currently are correct. Everything looks good. For this one right here, the chlorine is the highest priority substituent, and then this carbon up here that's connected to a bromine, and then the carbon that's just connected to a hydrogen. So this looks to me like it's rotating in a counterclockwise fashion, and therefore the label should be S. But the hydrogen is on a horizontal line in a Fischer projection and is therefore poking towards me, and so I'm looking at it backwards. So rather than redraw everything, I just flip the label. So if I'm looking at it backwards, if it looks like it's S, then it should actually be R. Okay, so this is the Fischer projection for 2R, 3R, 2-bromo, 3-chlorobutane. 1 down, 3 to go. And we need to do this faster, and we also need to do it without using ChemDraw 3D. And so this is where it's kind of nice to think about a stick figure diagram. So I'm going to go ahead and draw this little guy right here. He's going to have his head and his feet. Well, those will be arms. And then we'll have feet down here. So this is my stick figure. And so rather than take this molecule and rotate it every which direction, I'm going to use this person right here, and I'm going to rotate. I'm just going to move them and put them in the correct location so that they are looking at the Fischer projection correctly. I also want to give him a little eyeball. Okay? Try not to make it too creepy. Oops. There's evidently I got to make an eyeball of a certain size. Okay, so we'll make this the head right here, and then this is the eyeball. Okay? And this is important. Stick with me. Okay, let's go take a look at what's going on with this Fischer projection. When I look at, let's move some stuff around so I can get my Superman in the correct orientation relative to this molecule. For this compound right here, what you do is, and you can do this with a piece of paper and rotate it, but you want to look at each of the chiral centers such that the carbon is puckered towards you. Right? So remember that you think about drawing a straight line from carbon number 1 to carbon number 3, and this carbon is currently puckered up, which means that this stick figure is looking at that carbon in the correct orientation. And as long as you take that stick figure and you point that stick figure's feet towards the higher numbered carbon and the head towards the lower numbered carbon, then you actually have just taken your stick figure and put them in the correct orientation to be looking at the Fischer projection. So if you could put yourself in that position of the stick figure, and that bromine, relative to your perspective, were coming out of the plane of the screen, that bromine would be on your left-hand side. And the hydrogen going into the screen, if this is where you were kind of flying over the molecule, then that hydrogen would be pointing into the screen, and that would be on your right-hand side. So rather than use ChemDraw 3D, I just think about the world from the perspective of a stick figure. Now, if I take that stick figure and try to look at this carbon right here, right now I'm looking at it backwards, because you need to be looking at that carbon from the perspective of the pointy side of the carbon. So I need my stick figure back. I'm going to take that stick figure, and now I'm going to flip the stick figure. And I'm going to be looking at this carbon right here at the pointy side. So I'm looking at the point edge of that carbon, where it's puckered towards me. And if you're laying on your back with your feet pointed towards carbon number 4, because that's the higher number carbon, and your head pointed towards carbon number 2, because that's the lower numbered carbon, then right now you have adopted the correct orientation to describe a Fischer projection. This chlorine is coming out of the plane of the surface that we're the two-dimensional screen that you're looking at. And if you're laying underneath this thing looking up underneath it, and that chlorine is poking out at you, then that means it's on your right-hand side. And the hydrogen's going away from the screen, and therefore, relative to this stick figure, it's on the left-hand side. So let's see how that works. So we have this compound right here. Okay. I'm done drawing the Fischer projection for this one. So there it is. So I'm one down. And now I'm going to take my stick figures, and I'm going to shrink them a little bit to make this easier to manipulate. And I'm going to make 2 of them. I'll flip it vertical. And then actually I'm going to take one more just to kind of show you that it does matter which direction you point your feet. Okay. All right, so for this compound right here, I need to figure out what the Fischer projection for this carbon right here should look like. Okay. I'm going to take this same model of a Fischer projection and just repeat it over and over again, because the backbone is going to look more or less the same. It's got a carbon coming out this side, and this side, and that side. There we go. Okay, so in order to see this carbon correctly, I need to make sure that my eyeball is pointed towards, it kind of matches. So if this carbon is puckered up, then I need to look at that pucker directly. So this is the stick figure that I need to be right here. I need my head pointed in the direction of the lower numbered carbon, carbon number 1, and my feet need to be pointed in the general direction of the higher numbered carbon, carbon number 3. Looking down from above at this compound, from the stick figure's perspective, that bromine should be on the right-hand side. It's going into the screen from the stick figure's perspective. That bromine is on the right-hand side. And the hydrogen would be on the left-hand side. And the stereochemical label popped up. It's S, so I've done that correctly. Now, let's take that stick figure and see what happens if you move, instead you put your feet the wrong direction. So here I'm looking at the puckered side of the carbon, the part that points up. Sometimes I refer to this as, you always want to look at the carbon so that it's going to poke your eye out. So if you get rid of the carbon, now you see that's kind of a pointy edge right there. That from the carbon to the carbon right there, that's kind of a jagged edge. And so if you were to impale your eyeball on there, that would be the right perspective. But right now my feet are actually pointed towards the lower numbered carbon. This is carbon number 1. You need your feet pointed towards the higher numbered carbon. And so because my feet are pointed the wrong way, when this stick figure looks down on this carbon right here, that bromine would be on its left-hand side. So it would be wrong. That's why you need to make sure that you orient the feet and the eyeball in the correct position. All right, so now for the other carbon, and let's go ahead and get rid of the letter C so you can kind of see that, well, this is the sharp edge of the carbon right here. It's puckered this direction, and you want to be looking at it in such a way, that if you were to push this person into that carbon, you'd put their eyeball out right there, okay? So this person is looking up at this carbon. The feet are in the direction of the higher numbered carbon, the bottom of the chain in my Fischer projection. And from this perspective right here, the chlorine should be on the right-hand side. And that matches up because the previous stereoisomer that I had, I didn't mess with that chiral center right there. Okay, well, yeah, hopefully that's helpful, because if it's not, I don't know how else to show that to you. We don't really need to look too hard to figure out what the last two are going to look like. I'm just going to take this model right here, and to get from RR to RS, I just have to flip the third carbon. So I'm going to take this carbon over here, and I'm just going to flip the hydrogen and the carbon, and that chiral center matches up. And so that's this stereoisomer as a Fischer projection. And now I'm ready to show the last stereoisomers. So I'll grab, copy and paste this over. And since this carbon is supposed to be S, that's carbon number 2, the one with the bromine, and it's actually R, I need to just change those. So I'll just move the bromine over and the hydrogen and just kind of flip them over to the opposite sides. And then I got to do the same thing here. I'm just going to flip my chiral center right there, and there's my last two Fischer projections. So I have RR, SR, RS, SS. Those are all four of the stereocenters for this molecule. Bottom, and that makes them a little lined up better. That looks prettier. You can also distribute them horizontally. This kind of spaces them out nicely. Not that anybody really should care, but I do. So there we go. The Fischer projections for all four stereoisomers of 2-bromo-3-chlorobutane. Question number 3. Let's look at D-galactose, and we're going to look at D-galactose and D-mannose. These are common carbohydrates. They are stereoisomers of D-glucose. And I'll show you the structure of D-glucose. There's actually a template that gives it to you. We can go down to the hexoses and pull out D-glucose. And there's D-glucose right there. Now, if you look at the difference between D-glucose and D-galactose, that chiral center has stayed the same. We can actually verify that by putting the stereochemical label on there. This chiral center has stayed the same. So this chiral center has changed, and this chiral center on the very bottom has stayed the same. That term D actually refers to this last chiral center right here. If the oxygen is on the right-hand side, it's referred to as a D carbohydrate. If it's on the left-hand side, then it's an L carbohydrate. And that's a biochemist. The biochemist came up with that system of nomenclature. The organic chemists use R and S labels because we're better than biochemists, but that's how it is. My degree is actually biochemistry, but I did mostly organic chemistry. Okay, so this is D-glucose. Notice how I have flipped one of my chiral centers to get from D-glucose to D-galactose, but not all of my chiral centers. And if you flip some, but not all of your chiral centers, then that means that these molecules right here are not enantiomers of each other, they are diastereomers of each other. If you look at D-mannose over here, I flipped the first, did not flip the second, and then flipped the third, and did not flip the fourth. So I flipped some, but not all of my chiral centers. So D-galactose and D-mannose are also diastereomers of each other because I flipped some, but not all of the chiral centers. So we have D-galactose and D-mannose. It asked me to DTR them. So this is, I flipped some, but not all chiral centers, so they are diastereomers of each other. And for the sake of your own note, you should probably explain that diastereomers. And this is because we flipped some, but not all chiral centers. All right. How many stereoisomers of D-galactose are possible? Well, at least two. There's D-galactose itself and D-mannose. Right? They're both shown here. But going back to that equation I showed you earlier, it is, we take 2 and we raise it to the power of n, where n, and in parentheses I'll put where n is equal to the number of chiral centers. Chiral chemistry. Muscle memory was typing that right there. And that tells me that I have 2 raised to the power of, and there are 4 chiral centers that are labeled for you. 2 to the 4th right there. And 2 times 2 is 4, times 2 is 8, times 2 is 16. So that means that there are 16 total stereoisomers in the family. The question asked is a little weird in terms of how the question's worded, and I would have to be more careful on an exam. But D-galactose is one of those stereoisomers. So technically the correct answer to this question is 15 stereoisomers of D-galactose, because the 16th one would be D-galactose. So I'm going to go ahead and identify that the correct answer is 16. Sorry, the correct answer is 15, but it's related to the number 16 because that's the number of total stereoisomers. Total. And 15 of stereoisomers are of D-galactose. So there's 14 more stereoisomers besides the 2 that I've drawn. One of them is called L-galactose. So the L is a biochemical definition of enantiomers. That's essentially how biochemists refer to enantiomers in the carbohydrates, is they call one of the enantiomers D and they call one of the enantiomers L. And so this question right here is more of just kind of a biochemical nomenclature question, that L and D forms of the same carbohydrate are enantiomers of each other. We'll see if over the course of this semester my typing skills get any better. I doubt it. Okay, that's it. Now, one of the things that I would encourage you to do in all of your spare time in life is to actually go through and check all of these chiral labels right here to see if you can come up with why it is the chirality that it is. And I'm going to show you the first one right here because that CHO is a little tricky. So here I have D-galactose, and let's go ahead and just kind of strip it down and just look at this one carbon right here. So I'm going to get rid of the rest of these stereochemical labels so they don't clutter up my life. I just want to see if this carbon right here is really and truly R like it says it is. But I want to take a second and redraw this CHO with a little bit more detail. CHO refers to a particular functional group called an aldehyde. Aldehydes are the highest priority functional groups that you'll encounter ever in Chem 351. And the only thing that means to you is that we're going to call this carbon right here, this is going to be carbon number 1. The carbon on CHO in carbohydrates will always be the number 1 carbon, and so this is the carbon that should be at the top of all of your Fischer projections, this aldehyde carbon right there. Okay. Now, in order to determine that this is indeed R, I need to assign priority to the remaining 4 atoms, so all 4 of the atoms that surround that chiral center. And so coming off of this chiral carbon, I have an oxygen, and that's going to get the highest priority. I have 2 carbons, and I'm going to have to figure out which one is higher priority. And then finally, I have a hydrogen right there. Okay? So I've got my first and my 4th priorities assigned when I need to come up with my chirality wheel. Let's now look at what the 3 atoms are that are coming off of this carbon right here. Okay? Coming directly off of this carbon, I have first an oxygen. Oops, should do capital oxygen. And then I have another carbon down here. So that's a carbon. And then I have a hydrogen coming off of this. And those are the 3 atoms that are coming off of this carbon right here. So it's got an oxygen, a carbon, and a hydrogen. Now, if you go up here and look at this compound right here, the way you have to think about this is when there are double and triple bonds, you end up counting those atoms twice. So coming off of this carbon is an oxygen, and then that oxygen is coming off a second time, and then we have a hydrogen right there. So now stacking the 2, we look for the first point of difference. Oops, I want to use this right here. The oxygens end up being the same, so that's not my point of difference, but that is my point of difference. The second bond to this oxygen right here takes priority over the bond to that carbon. So because this oxygen out-prioritizes this carbon, that means that this carbon right here has higher priority than the carbon on the bottom. And we're going to go from the highest priority, the oxygen, to the second highest priority, to the third highest priority, and this looks like it's rotating in a counterclockwise fashion. Okay, things that rotate like this are counterclockwise, and they should be S. And so why is it R? Well, that's the goofiness of Fischer projections for chiral centers. Kahn, Ingold, and Prelog did not communicate well with Emil Fischer when they came up with Fischer projections, because if you remember, everything that's horizontal in a Fischer projection is actually poking towards you. And if the hydrogen, which is supposed to be going away from you, is coming towards you, rather than attempt to redraw the entire compound, just assign it, just do the circle like we normally do it, call it S, and then remember that the hydrogen is backwards, so flip your label to R. So I've just verified to my satisfaction that that first carbon's chiral center label, as shown in ChemDraw in the document, is correct. All right, let's finish up our definitions. Stereoisomers are compounds with the same connectivity, but different three-dimensional arrangement. Okay. And then the last one that we haven't defined yet are diastereomers, and we're not going to use the definition that they're not enantiomers. We're going to use the working definition that they are compounds where, so they're actually, we have to remember that they're stereoisomers of each other, where some, but not all, of the chiral centers are flipped, rearranged, or inverted. Okay? And while we're at it, let's go ahead and add in this other definition where in stereoisomers, enantiomers are also stereoisomers where all chiral centers are flipped. Okay? And if you remember these second definitions, you'll be right almost every time, especially in this class, and you'll save yourself a tremendous amount of headache trying to draw superimposable images. Okay. For this compound right here, the chalkboard problems that I'm going to ask you guys, you just need to come up with the chiral configurations right here, and there are actually 4 different answers that you should post as chalkboard problems. So question 1 actually has 1.1, and then somebody else can answer 1.2, and then 1.3 and 1.4, etc. And then what I need you to do is, looking at this glucose molecule right here, go ahead and break out your Superman and figure out how to look at this so that you can generate a Fischer projection of this. And I think this is D-glucose. I'm not sure. The D and L refer to that last chiral center. So if you draw a Fischer projection of this compound and that last chiral center ends up on the right-hand side, then yeah, you've got D-glucose. If that last chiral center ends up on the left-hand side, then this compound ended up being L-glucose, and you just need to draw the enantiomer for it. Or you can probably just Google Fischer projection of D-glucose and not learn anything and post a correct answer.